Welcome back, Cosmic Explorers. Caroline here. Today, we're going to start with one of the most iconic images in all of astronomy, the Pillars of Creation, taken by the Hubble Space Telescope in 1995. It's one of the most famous and widely used images NASA has ever produced. But what's really going on in the picture? What are we actually looking at? These towering clouds of gas and dust stretch light years tall, glowing with eerie colors. But what makes the image so special isn't just its beauty, it's what's happening inside those pillars. Hidden deep within the clouds are the cradles of newborn stars. Thanks to images like this one, we can have a front row seat to the birth of a star in stunning detail. Today, we'll journey into these cosmic clouds and uncover the dramatic process of stellar formation. Let's zoom in on the earliest chapter of a star's life. So what exactly are these massive clouds where stars are born? They're called nebulae, vast regions of gas and dust floating through space. But these aren't just wispy, random leftovers from other events. They're packed with the raw ingredients needed to build a star, which is why they're sometimes called stellar nurseries. For example, the Carina Nebula, shown behind me, is a major site of a star birth within the Milky Way galaxy, with numerous young stars and star clusters forming within its clouds of gas and dust. What raw materials do you think are necessary to form a star? Surely we're talking about something really rare and complex, right? Actually, no. Do you remember which element primarily undergoes fusion in stars? It all starts with hydrogen, the most basic and common element in the cosmos. When the star is ready to begin fusion, two hydrogen atoms will fuse to form a helium atom, releasing energy. This is why there are a septillion stars in the universe. Their primary ingredient, hydrogen, is readily available. But we're not quite ready for fusion yet. Let's back up to before the star had formed. Inside these nebulae, gravity gets to work first. In a process known as gravitational collapse, small clumps of hydrogen gas begin to attract more and more material, slowly pulling it inward. But it's not a smooth or gentle process. As the gas collapses, pressing more and more matter into a smaller space, what do you think happens to the temperature? It begins to heat up as the pressure increases. The core of the clump gets denser, hotter, and more chaotic. Eventually, the collapsing clump becomes so dense that it forms a protostar, a kind of pre-star that hasn't quite ignited yet. It's still gathering material, still heating up, and still hidden deep within its dusty cocoon. But this transformation doesn't happen overnight. The process of collapse and protostar formation can take anywhere from 100,000 to 1,000,000 years, depending on the size of the original gas cloud and how much material is available. So now we have a protostar, a dense hot ball of gas still buried inside its parent nebula. It hasn't officially joined the ranks of stars just yet, but it's getting close. As gravity continues to pull material inward, the protostar keeps growing. It begins to spin. This spinning motion causes the gas around the protostar to flatten into a rotating disk, which will later play a big role in the formation of planets. Inside the protostar, things are getting intense. The pressure and temperature keep rising as more material piles on. The gas particles are moving faster and crashing into each other more violently. Eventually, when the core reaches a temperature of around 10 million degrees Celsius, something incredible happens. Nuclear fusion begins. This is the moment that establishes our protostar as a main sequence star. Its size, color, temperature, and luminosity now become set, determining its classification. So a star is officially born once fusion begins. But why can fusion only begin when the temperature reaches 10 million degrees? You might remember from a previous lesson that hydrogen atoms don't easily stick together, which is required for fusion. Hydrogen nuclei are positively charged, and positive charges repel each other. So for fusion to happen, the particles need to be moving extremely fast, fast enough to overcome that natural repulsion. That's why the temperature needs to be so high. Only in those extreme conditions can the hydrogen nuclei collide with enough force to merge into helium and release energy. But thanks to the increasing temperature from the ongoing gravitational collapse, we're there. The outward pressure from this fusion balances the inward force of gravity, so the protostar is no longer collapsing. It's now stable, shining, and officially a main sequence star. From this point forward, the star will spend the majority of its life in this balanced state, steadily fusing hydrogen into helium in its core. How long that phase lasts depends on the star's size. A massive star might burn through its fuel in just a few million years, while a smaller star, like our sun, can shine for billions of years. Stars aren't born in isolation. They often form in massive, chaotic environments called stellar nurseries, like the pillars of creation that we saw at the beginning of today's lesson. These regions are full of gas, dust, shock waves, and radiation, all of the ingredients needed to form a star. And there are different types of nebulae. Emission nebulae glow with vibrant colors, emitted from the large amounts of hydrogen gas in young forming stars being excited by UV rays. Reflection nebulae don't glow on their own. They shine by reflecting light from nearby stars, often with a cool blue hue. Dark nebulae, on the other hand, block the light behind them entirely, appearing like inky voids in the sky. But don't be fooled. They're full of potential, hiding the earliest stages of star formation. What type of nebula do you think the pillars of creation represent? Newer images taken from the James Webb Space Telescope allow us to see the region in even more stunning detail. Do you think it's an emission nebula, reflection nebula, or dark nebula? Pause the video for a moment and make your prediction. This one isn't as obvious as it may seem at first. The pillars of creation are actually part of the larger Eagle Nebula, which is considered to be an emission nebula. The glowing gas around the pillars is ionized hydrogen, lit up by the intense ultraviolet radiation from nearby young hot stars. This is the hallmark of an emission nebula. However, some astronomers consider the pillars themselves to be an example of a dark nebula. The dark, dusty columns appear in silhouette because they are cooler, more dense regions of gas and dust, making them dark nebulae embedded within the larger emission nebula. So you can give yourself credit if you picked either of those options. Another famous stellar nursery is the Orion Nebula, close enough and bright enough to be visible with even a simple telescope. In our night sky, you'll find it in the Orion constellation. Look just below Orion's belt. What looks like a star at first will reveal itself to be much more through a telescope. Studying the Orion Nebula has given astronomers groundbreaking insights into how planets form alongside stars, as well as how the complex motions of gases affect star formation inside these nurseries. So how do we know all this if we can't actually see inside a nebula due to their thick clouds? Well, seeing is a tricky term because we usually assume that we can only see visible light. But do you remember learning about the other types of light waves? Which type was especially good at passing right through clouds of gas and dust? Infrared. Astronomers use infrared telescopes, like this one on top of Mauna Kea in Hawaii, to peer through the dust. Look at the difference between a visible light image and an infrared image of the Lagoon Nebula. Infrared light can pass through clouds that would block visible light, allowing us to detect the warm glow of baby stars and see with great detail the processes occurring there. These infrared views give us valuable data that reveal how common and how dramatic stellar birth really is. Star formation is one of the most important processes in the universe. It creates light, drives the evolution of galaxies, and sets the stage for planets and possibly life. Every star you see in the sky tonight began in this way. Remember that it all starts with gravity pulling material together. As it draws together, the pressure causes it to heat up, and eventually, it's hot enough to begin fusion. It's a process that repeats itself over and over throughout our universe. So next time you see a mesmerizing photo of a nebula, remember the story behind its glow. But if this is how stars begin, what about the other bookend to their story? Next time we'll take a closer look at how stars die. Until then, keep marveling at all the mysteries in our universe.
Hey, hey.